We'll move on next to Professor Cath Noakes. Hi, Cath. Cath Noakes is Professor of Environmental Engineering at the University of Leeds. Her research focuses on airborne infections and transport of airborne pathogens. Like Julia, she's also been a member of SAGE and chairs the Environmental and Modelling Group, which has provided evidence to government on mitigation strategies for building to minimise risk of COVID-19 spread. So she's going to give us an overview of all things related to the impact of environmental factors on transmission. So thanks very much, Cath, and with that, I'll pass over to you.
Thanks, Cara. And yes, thank you for inviting me to talk about this. So my background is in engineering. I originally started life doing fluid dynamics and thinking about airflows in buildings particularly. But have thought to some extent about how we can model some of this, although albeit not with quite the same level of maths as many people here. So I'm trying to make this work. There we go. So I wanted to just start off by thinking about the modeling scales, and I think I guess we can group these into probably more than one scale, but I've sort of suggested 3 different groups here, where we've got the population scales, where we've got the epidemic models. We're basing a lot of that information on observed transmission, and things like contact rates are taken from the observed transmission, and we can, as Julia sort of spoke about, we can extract quite a lot of that information now, but we are missing some things around those physical mechanisms. Then there are models which are often quite hard to do, again because of lack of data and things, but about how we might model, I call it building scale here, but it might be a small community or a very small group of people type scale. And there are a number of attempts in here, sort of trying to link the environment to transmission models. We can do these through compartmental models or agent-based models, and I know you'll hear one from Nick Warren at HSE later on in this session. So these ones I think start to tell us what might happen in amongst a small environment, but are again they don't quite have the mechanistic bit of what the actual transmission is in there, and these ones are probably very challenging because they're quite highly stochastic. I think you've got to really deal with those small numbers and that variability. And then really where I sit is in this micro scale, so thinking about the actual physics of how transmission happens and thinking how we can develop appropriate mechanistic models of these with a sufficient level of detail to encompass what actually happens in transmission, but at a high enough level that we can try and interpret some of the key parameters out of it, rather than just getting stuck into the real detailed physics. And I think probably Julia highlighted this in her talk, really, that there's a big challenge about how we connect these different scales together. And I think that's not just in the fact that they are models at different scales, they're also models that traditionally different communities of researchers have worked on, from the microscale models, which have been driven often by physics and engineering researchers, through to the population scale models, which have come much more from the mathematics and epidemic modelling. And I think there is this really interesting thing about how we connect these together and probably do the bit in the middle well. So I'm going to talk about the microscale and just touch on how we can connect some of these. If we start thinking about transmission dynamics for a respiratory infection, obviously it would be different for other diseases. We do know we've got somebody who has that infection. They are our respiratory source. They will emit virus in aerosols and droplets when they talk, they cough, they sneeze, they just breathe. We know that they'll emit different amounts under different circumstances. We may also get emissions from treatment in hospital, so certain procedures could enhance or decrease emissions. And there could potentially, for some diseases, be environmental sources as well. So particularly where things are on surfaces or where things could get resuspended in the air, there might be a source there. Whatever it is, if it's going to be released into the air, it has a size distribution of particles that carry that virus, which is an unknown, and it will happen at a particular location and for a certain duration of time. And I think we shouldn't just assume that somebody who's infected continually emits virus. They may emit some for some of the day, but not emit or barely emit any for other parts of the day. Once we've got that virus emitted, it's then essentially a fluid dynamics and transport problem as to how those particles get transported in the air or through the environment via people. Some will deposit, some will be carried, and then eventually will expose another person. And that exposure, again, we suspect there are different exposure routes. You can inhale those aerosols, so you can inhale particles up to about 100 microns in size, and you can inhale them when you're close to somebody. And some of these aerosols, the ones which are below about 10 microns in diameter, will transfer large distances in a room. So beyond 2 or 3 meters, you can inhale them depending on ventilation. But then we also must forget other routes of transmission. So large droplets might deposit onto surfaces, and then you can touch those, contaminate through hands by touching your eyes or your mucous membranes, or even just direct deposition. I think we've probably all met a spit talker where you get hit in the eye by something. Don't like to think about it, but it's rare, but it happens. And I think this is complex in itself, because in here we've got to think about the virus itself. What's the characteristics? How does it survive? How does it survive under different temperatures, humidities, different environmental conditions? We've got to think about the human characteristics, so who's interacting with who, and that is really hard to work out because we make an awful lot of assumptions. And then quite possibly the easier one of the three is understanding the fluid dynamics. I mean, that's hard, but I think at least we've got some laws that we can draw upon to enable us to model that. And when we're thinking about these different stages, there are a lot of factors that influence it. So for example, in the emission rate, we've got the viral load, the aerosol size range, and the activity that people doing. And then we've got the fact that they're wearing masks and they might have different hygiene behaviours in there. The environment itself, we've got ventilation, which is, obviously seen as quite a big thing at the moment, as the main one which will control aerosols, but then also distancing, which you could argue is a behavioural one, you could argue is the environment. We've got whether the virus survives, and particularly the temperature, humidity, UV conditions, and then actions that we might take in that environment, like cleaning the environment. And then when it comes to being exposed, there's a lot of human factors in here. So what hand hygiene do we practice? What mask wearing do we practice? How frequently do we touch our faces and surfaces? And what breathing rate do we have? And how does that vary with activity? And then once somebody is exposed, what is the efficiency of that virus depositing in a person? So, is a virus that is inhaled equivalent to the same virus that is deposited by a finger on the eye? We just don't know. And then once we've got that, what is the dose response from those that viral exposure in the environment? So just starting by thinking about the air, I'm going to think about the air first of all, because actually it is the easiest one in some senses to put together a simple model. You can do some really simple mass balance models to look at concentrations of virus in air. So E would be the emission rate of a virus from a person. There would be in a room which has a volume V. The concentration C is the concentration in air of virus or per maybe plaque forming units per cubic meter in there. And then we've got a bunch of loss rates in there. So we would have loss rates because of ventilation, and that might be the ventilation from a natural ventilation, so opening a window, for example, QN. And you've also got leakage ventilation. All rooms have a certain amount of background leakage as well. You'll have a loss rate to do with deposition onto surfaces. So depending on the particle sizes, you'll get different deposition rates. You'll have a loss rate, which I've written in here which will be the viral decay rate with time. And then you might have a loss rate due to a recirculating ventilation system or an air cleaner, which would have a filtering rate in there. So, I mean, all of these loss rates you can quantify in some way, and it allows you to get an understanding of either the steady state or transient viral concentrations that could be present in that room. And then, of course, the exposure that somebody might have when they're in that room depends on the concentration in the air, the rate at which they inhale, and the time they spend in there. And of course, this is a simple model. This assumes an awful lot of things, including probably the biggest assumption of all, which is that this virus is uniformly mixed in this space. And we know that in reality, that will not be the case. But actually for people in a reasonably well ventilated or well mixed room where you've got people who are more than a couple of meters from the source, it's not a bad estimate, certainly to at least give us an understanding of the different parameters. Thinking about the emission rate, this is probably the hardest one to do, because first of all, we have to make a set of assumptions. So the assumptions that most of us are working on at the moment is that the emission rate of virus is a dependency on the viral load, the aerosol emission rate and its size distribution, and of course the duration of time by which somebody emits that for. And at the moment, we're very much assuming that, the virus is distributed by the volume of particles that people breathe out. I think there is data starting to come that says that might not be the case, that it might be preferentially in smaller particles compared to larger ones, but it's a bit hard to say because, I think we need an awful lot more data before we can say that is or isn't the case for this virus. But essentially, even within these, you've got, for the viral load, you've got the inherent viral load that an infected person has, plus you've got the stage of the infection that they're at. So their, CT value will vary because of their own in-host dynamics and because of the stage of infection. And we can just perhaps take a distribution and assume that if any infected person, we can pick a point on that scale, that distribution, and say that they have that viral load. The emission rate, again, is pretty hard. We know that there's a considerable variability between people and between activities. So if some people will breathe out, will exhale as much or many aerosols when they're breathing as another person does when they are coughing or singing. So we know that on the whole, activity increases it. So you've got far more aerosols emitted when you talk and then when you sing or shout loudly compared to when you're just breathing. But say there's a huge variation between people. I think as your breathing rate increases, you will also emit more aerosols. And then what happens to those aerosols when they get into the environment will depend on factors like the temperature and humidity of that environment. So the lower the humidity, the smaller the particles you'll get and the further they can potentially go. And also whether somebody is wearing a mask and how well they're wearing that will change that emission rate. So we've got a huge variability in here. And I think this probably is going to vary over at least 4, if not 6 or 7 orders of magnitude. And I think that's one of the things that makes this incredibly challenging, that we can't just pick a single number to say this is the emission rate for a person. If we do have that sort of information, so we can encompass some of that variability in emission rates with variability in the ventilation, the duration of exposure, sizes of spaces, etc. And we can do some ideas of relative exposures for somebody with a comparable viral load in different settings. And so with this model we did here, where we looked at a simple aerosol mixed ventilation model, and compared it for a set of classrooms, which are the first few here, with different, the numbers here, 750, 1,000, 2,000, etc., represent the CO2 concentration you will get at steady state in those classrooms for the ventilation rate. We've got offices which are a normal office and one with a poor ventilation rate, and all of these assume a whole day of exposure. So everything's sort of relative to this benchmark classroom, which was at 1,500 parts per million. We've then got some here which have got a coffee shop and a supermarket, which come out much lower, and simply because you're only in there for maybe half an hour compared to being in these settings for several hours. But then when you go in a gym, even though you're only in there for a fairly short period of time, the relative exposure goes up again because of the activity that's increased the viral emission. And then we have got some from some outbreaks, so Guangzhou restaurant outbreak, Skagit choir, which I'll talk about in a minute, which comes out really high. That was over a couple of hours, and a German meeting, which was another super spreader outbreak very early in the pandemic. So this is a way of trying to look at the relative exposure by thinking about what happens to those aerosols in a space. We want to link it to the risk of infection. That starts to get a bit trickier. So we can take that exposure and then apply a dose response model. At the moment, I don't think we've got one that's good enough, or that we're confident is good enough for this virus, but there are a couple for other coronaviruses. And where we have used these so far, we've been using either HCOV 229E, or we've been using a hybrid between that and SARS-1. Another approach which some of you will have come across before is Wells-Riley. So Wells-Riley is a little bit of a cheat. It basically encompasses the exposure and dose response into one model and allows us to try and predict the number of new infections based on some environmental parameters. So if you've got susceptibles, S, infectors I, you've got a ventilation rate in a room, which will be Q, you've got a breathing rate, P, the duration of exposure, and then this parameter called quanta, which is essentially how many infectious doses each person generates in a unit time. And that, I suppose, encompasses the viral emission rate and the dose response in together. This is written in a way that's a steady state, assuming a steady state quanta. You can write this in a transient quanta generation as well. So it's not a perfect model by any means, but it is quite useful, and it's a useful way of thinking about the interactions of some of the environmental parameters. Just to give a feel for sort of typical quanta values, they tend to be back calculated from outbreaks, which in itself brings a big challenge because you don't always have the right data to be able to calculate that. But you can see some quite big variations. So for TB, we're in relatively low, but we do see some super spreader ones from some human to guinea pig studies where we've got some much higher values. Measles tends to be very high. This is a school outbreak, but again, there's very little data to get lots of measles outbreaks to be able to calculate this. Some variations, influenza, you can see some quite big variations, and I think this one was particularly interesting that we looked at just last year, where we took some data from some human challenge studies, which was the bottom end, and then some wild type infections, and based on data from exhale breath sampling. And you can see again really quite significant variation, and I suspect this is telling us that there's a hell of a lot more variation in most respiratory infections than many of the outbreaks in the past have led us to believe. In terms of SARS-CoV-2, it's very hard to gain an estimate. There is a fairly nice study that was done early on where Giorgio Buonanno and colleagues tried to estimate quanta by looking at the viral load and aerosol generating activities, and they actually calculated some really big ranges, although most of the time suggested it was probably going to be somewhere between 1 and 100 quanta per hour. The different lines on here represent different respiratory activities, so ranging from breathing through to some singing and loud and talking activities. And I'll show you the Skagit choir one in a minute, but that we got some really quite high estimates, which puts it in a category of you know, super spreader measles type outbreak. Yeah, so the Skagit choir one, which again I suspect many of you know this study, but it was a choir rehearsal with 61 people. They got 53 suspected new cases from it. 33 were confirmed positives, but there was the other 20 had symptoms. One infector in there, mildly symptomatic. The infections were spread across the room, and the index case was actually stood at the front. They didn't have anybody in front of them at all. So you know, the difficulty with this one is there were some other interactions. Although they did use hand sanitizer, they didn't have hand contact. You know, they did put the chairs away at the end of the rehearsal, and they did, apparently there were some oranges that some of the people had, but not, only about half of them had. So it's surprising that if it was the oranges, you'd think there'd be more, it would only show up in those people. But we had a go at modelling this one. We got quite a lot of data from the choir themselves about the room they were in, about the timings, and we made some estimates using a Monte Carlo version of the Wells-Riley equation. And we're able to estimate a quanta emission rate. The central estimate's about 970 quanta per hour, but there's quite a big range in here from 550 up to 1500 quanta per hour. We estimate that the rehearsal was very low loss rate, which is equivalent to air change rate, ventilation rate here. So we believe it was somewhere down in this sort of very low ballpark. And of course, if you then start saying, well, what happens if you increase the ventilation rate? It predicts that you would get a lot lower probabilities of infection. And similarly, if the rehearsal itself was 2.5 hours in duration, which is the solid line here, but if you reduce that down to only half an hour in duration, you predict a lot less cases. I mean, this one is probably the most extreme example that there is out there of a super spreader event. It's a very large number of people infected in a short period of time. But I think essentially what we've done here is put the risk factors all together at the same time. So the singing, the poor ventilation, the person with the mild symptoms at the highest, probably with a high viral load at the beginning of their infection. I've only talked so far about airborne routes. There are of course other routes in here as well. So when we're thinking about close transmission that happens at close range, it's much more complex because you're exposed to all the different sizes of particles, and you have to think through then the much more about the physics of that. And it's also very heavily going to be influenced by the particular emission rate of the person and their activity, the distance that somebody is from them, their orientation, so whether they're face-to-face or not, and whether mask wearing happens in there. I think what's probably less important for that close range transmission is factors like viral decay, because you are going to be exposed to their virus in seconds, not over hours. So although you might spend hours with them, the actual exposure where you probably inhale it happens probably very quickly before that virus has time to decay. The physics of this is pretty challenging though, and I've just listed a sort of set of models that people use there, and they range from a really sort of simple gradient where you just assume a change in concentration with distance from the source, or sometimes people modify that to say there's a cone of higher concentration where people are exhaling a plume, through to really quite detailed models of the full physics through a computational fluid dynamics model. The challenge, of course, with that is how do you then get that really complex physics model into something that's simpler to look at an epidemic type model. Fomites, I think, are actually even harder. So Obviously, we can get transmission of fomites through contamination of surfaces. That might be because the immediate deposition of droplets and then people touching them, but also people who are infected, we know from several of the studies that they have quite contaminated hands. I suspect people touch their nose, touch their mouth, they cough on their hands. It's probably quite an effective way of getting virus on your hands. And then, of course, that gets spread around the environment. Whether you are exposed via a surface is something that I think you can control much more readily than, say, an airborne transmission, because you can manage it by not touching your face. If you've got virus all over your hands, but you never touch your face, you never touch your eyes, you can't get it into your respiratory system off your hands. So it is very dependent on a human behavior, and that face touching frequency again varies hugely with different people, different settings. And we also don't know how much of a lot of data on face touching, but if you touch your nose or you touch your cheek, does that matter, or do you actually have to rub your eye or stick your finger up your nose or something? I think there's a lot of factors that influence it, and certainly when we've modelled this, you get some very big ranges, because you've got a whole factors, all the emission factors that we had before, plus you've then got all these additional behavioural factors, and you've got to factor in with these things like viral decay, cleaning, hand hygiene, because it's going to stay around in that environment over a period of time. And then when we start thinking about modelling, I know there's a CDC put something on their website about being a very low risk of surfaces, and I think that is true. It probably is a very low risk, and they said it was 1 in 10,000, but that was based on a single touch model. In reality, we have to think that we touch multiple surfaces day in, day out, and if you go to somewhere like a supermarket, you touch the trolley handle and you probably control that touch, and then you touch food packaging, which on the whole other people haven't spent a great deal of time touching. I guess somebody put it on the shelf. But when you think about your home, you share lots and lots of surfaces with everybody else who lives there, and you can't get away from that. We can't possibly clean our hands enough and clean our surfaces enough to stop that, and we probably wouldn't want to. It would be just infeasible. But I think it is important to factor that in, that we do touch a lot of surfaces, and what we don't know is how much that matters for this virus, or how much. But I think for some diseases it certainly does matter a great deal. I do want to just talk briefly about some work we've been doing on modelling public transport, because this gives an idea of how we've been looking at the multi-zone, multiple route risks. So this is something called the TRACK project, which is APSRC funded. We're trying to model typical journeys and looking at the aerosol, close range and contact transmission, and feeding that with data on human behaviour, interactions on public transport, some understanding of how much virus or viral RNA is present there, and the environmental side from ventilation perspectives. And I'll just show you a little bit about the risk model in here. So the base model is drawn from a paper from a few years ago on cabin air for on an aircraft, which is a stochastic, what's called QMRA, or quantitative microbial risk assessment model. We assume that we have a particular respiratory activity, so we take that from a set of aerosol emission models. These models actually have a fixed single viral load in, so we haven't got a variation in viral load. And then we model 3 different routes of transmission. So we model airborne transmission through very small aerosols that have a dry diameter of less than 5 micron. That means they actually start bigger than that, and we let them shrink. And we assume that it's fully mixed with a ventilation based on the carriage data. We then have a fomite transmission route, where we actually say somebody has hand contamination and we get a deposition contamination. And then we assume that passengers touch certain surfaces during boarding and alighting. And then we use a transmission model to look at I think it's a Markov chain model in there, to based on the surface contamination with hand area and transfer efficiencies to and from surfaces. And then we have a close range model where we consider passengers who are within 2 meters of an infected passenger. We define some zones at 1 meter and 2 meter. We don't model the actual position of people in this case. We just put a loading in and then a proximity based on the passenger density in the model. And those people at close range are getting exposed to all the sizes of aerosols rather than just the small ones. And we use a loading data, so it is an agent-based model. So we have a loading approach whereby, you know, an infectious person can get on at one stop, and then we can identify people who are within the particular ranges. So the graph on here has got our infectious person who's on for between stops A and F in this case, who are in red, and then you can see where we've got passengers in here who are within 1 meter and 2 meters of them, and then the rest of the passengers are further away from that person. And of course, once the infected person gets off, all of these go green because it's then just the residual of anything in the air in that environment. So just to give you a sort of feel for the types of results that we can get from this, this is the looks at all of the exposure to the total dose from all of the different routes, and this is the effect of different loading on that carriage. And what you see is that it's quite highly stochastic. The mean, which are the triangles, are quite influenced by these small numbers of outliers, and the outliers are actually very high doses from either fomites, so a very small number of high dose fomite routes, or the close range transmission when somebody happens to be close to you. Whereas the median shifts from very small to, and it jumps at about 50%, and the median is much more influenced by the air rather than these outlier doses. And just to show you a bit more information on this, we can start to split it down. So it's slightly complex plots here, but we've got waffle plots which show in these are the origin stations and destination stations. And this is a particular case where we've got 2% prevalence of virus in the population, 100% loading of the carriage, and we've got nobody wearing a mask here. The BLO is a particular aerosol source model that we've used, and this particular seed, this case, has got has ended up with 4 infectious people who are the orange dots, and you can see the duration of time there on the carriage of the orange lines, and then the green dots show you the total dose of virus that people would be exposed to in here, and the little ticks on the side show the different doses received by different passengers on that journey. And what you see is once we put the masks on, that we get quite a shift. We lose a lot of those outliers, the high cases, and they drop right down, and we get a general shift downwards in the total dose of virus on this one. But we can actually then split this up by the different modes of transmission. So when we look at close range transmission without masks, we see that all of these doses are sitting really high. These are the outlier doses, and these are the ones which are, you know, where people get that high exposure. Put the masks on those people, we've dropped those down quite significantly, because although people are still close, we've got quite a significant shift in that exposure. When we look at fomite doses, again we see these outliers. We see some clusters of a few high cases, some middling ones, and some lower ones. But once we put masks on, we lose some of those high those outlier cases, and they drop off. And then in the case of the airborne doses, we see these are much lower overall, and they don't change that much. So the masking changes it a little bit, it shifts it down slightly, but the masks are less effective against the airborne stuff. I should say that the airborne comes out quite low in this model, and the reason being is it's very highly ventilated. It's got quite a high ventilation rate, which gets rid of anything in the air pretty quickly, and also it's quite short duration journey time. So I think we'd see this play out slightly differently if we did it over a longer journey with a lower ventilation rate. Just to finish off, because I'm conscious of time, I just want to talk about a little bit about how we can connect some of these infection risk models to an epidemic model. So some work from a number of years ago where we looked at taking the Wells-Riley model and basically connected into an SCIR model, and did this in really quite a simple way, where we took the contact rate from the SCIR model and said, okay, well, the contact rate is actually now from the Wells-Riley model, so it's the breathing rate, the quantum emission rate, and the ventilation rate. And I've realised now from listening to Julia's talk that we have embedded a generation time in here without realising we've done it. So I'm glad I listened to that bit of your talk, Julia. But at the same time, what that does mean is we can, although we've embedded a generation time, we have allowed it to vary because we've coupled the ventilation with it in. And I guess if we just plot the sort of very classic outcomes from an SCIR model, we can see that changing the ventilation rate, because it's changed the generation time, essentially has extended the duration of the outbreak, reduced the total numbers, and sort of flattened those curves out. And this, although is the deterministics, the means, it is a stochastic version of it. And if we look at the variability in this, the probability of transmission, or probability that we'll get a particular number of cases in this model for different quanta generation rates, then we can see that changing the ventilation rate from 3 air changes an hour to 6 air changes an hour, so this is like a hospital type scenario, you can see that the particularly where you've got lower quanta generation rates, but for all of them really, you shift the probability distribution to the left, and you are less likely to get a major outbreak in this. Now, one of the big limitations with this is assuming a fixed population who are in this hospital ward over 30 days, which is a little bit unrealistic in reality, but it gives you sort of an idea of how in a fixed setting this can work. This model, we also looked at trying to look at the trade-offs, because we said, well, actually, if you increase the ventilation, that brings you a cost. You've got a higher energy cost, but if you've got less infection, that also has a cost. So we looked at the trade-offs between the ventilation costs and the costs per case of infection. And what was quite interesting is we plugged in a bunch of numbers with a huge amount of uncertainty for both the energy and the infection cases, and by sheer chance the sweet spot sits at around about 4 to 6 air changes an hour, which is the current guidance for hospitals. And I was quite amazed that that was exactly where it landed, because it wasn't planned. The other thing we then could do with that was actually look at, the probability of an outbreak and the cost associated with the probability of an outbreak. And again, this starts to look at the trade-offs, which says, well, when you've got a low ventilation rate of 1.5 air changes an hour, you have quite a high probability that your outbreak happens. So you get quite a high probability of a high cost associated with it. Whereas when you go all the way to say 12 air changes an hour, you've got a low probability that your outbreak cost happens, but you've got a high probability that that you've got a high cost because your energy costs are so high. So really, you want something in between the two, which is going to reduce your costs of infection, but without going over the top in terms of ventilation. And last but not least, we did do a further piece of work where we took this Wells-Riley model and coupled it to an SIS model this time in a multi-zone ward, so rather than just a single zone ward. Again, this isn't for COVID. This assumes a much shorter incubation period. But essentially, what we're modelling here is that the probability that we'll get a particular number of cases of infection. So there's 18 patients, and you can see the infections are going to go from either 0 up to 18 in some of these cases. So it's the probability distribution that we get those cases of infection. The different coloured bars represent some different ventilation regimes, so different ways in which we put the air in and air out, even though the overall ventilation rate's the same. And then these numbers here, B to naught, is the amount of air that mixes between the bays in this hospital. So it's like 3 bays in a hospital, and it mixes. And what this is sort of telling us is that as you've got more mixing of the air between bays, it starts to stretch this out very slightly. But then this is assuming you detect your outbreak when your first person has symptoms. So if we detect it after 12 hours, you've got you're shifted to the left. But if we can't detect until 48 hours, then you end up with a much longer, a much more flattened out profile. And so again, I think these was really sort of toy data. It's more to give us an idea of how we can start to connect these things together. And I think there's, you know, it shows you can do it, but there's a huge number of limitations in these models at the moment in terms of how well they represent what happens in reality. So I think, just to finish up, I think we know that the environment can influence all of the modes of transmission, but the environment has the greatest impact on the airborne routes and fomite routes. Close range, even though it is an airborne transmission, it's a very close inhalation, and it's very difficult for the environment to actually impact on that. It's more individual behaviour there. I think when we're talking about ongoing transmission and of a pandemic, I think the airborne route is the most important one there, because it's where you can get transmission from one person to many people in quite a short period of time, whereas I think the surfaces, I suspect, play a much more minor role in most environments, and they're not driving transmission. I think where we can think about, does the environment, or particularly the ventilation in the environment, affect a generation time? I think where you've got, for example, settings where the same people regularly go in the same space, so a school, a workplace, a prison, etc., that's where actually it could shift things. It could change it from you have 1 or 2 cases to you have 10 or 20 cases. And then that, of course, then has an impact on ongoing transmission. I sort of wonder what happens nationally, and is some of the seasonal effect that we're seeing to do with ventilation rates or not? And if, you know, if you had a big national campaign, what would that do? Is that like masking everybody? But I think we need to think more carefully about how we model these and how we connect some of the physics models to the transmission models to allow some of these parameters to sort of feed through from one model to another. And at that point, a big thank you, because there's a huge amount of work in here that is not mine. Especially want to pick out DSTL track team, because they really did an amazing job with putting together some of the risk models that we've done for transport, and yeah, a whole bunch of other people who we've worked on with this over a number of years, not just now. And thank you very much.
Great, thank you very much, Cath. That was a really great overview of environmental modelling. So there's a question come through to the chats from Juan. So it says the quanta for SARS-CoV-2 seems to be comparable or higher than measles. So he asked if he read that right. And would it follow that there are cases, for example, the choir case, in which COVID's R0 would be comparable or higher than measles as well?
So yes, I think the quanta is probably incredibly variable for SARS-CoV-2, and I suspect it varies from less than 1 up to probably nearly 1,000. So the choir case is one where I think that probably is an extreme, but I think that is comparable to measles. It's quite rare to have a measles outbreak in an unvaccinated population these days, but or a population with no immunity at all. Whereas I guess in the early days of this pandemic, we were having outbreaks with zero immunity in the population. But I do think that one, I mean, we got 87% of the people in that environment who were infected. That's a huge number. So I think there are some of the outbreaks which are comparable to measles. I think most of the outbreaks, most cases are not though. Most outbreaks are much lower than that.
And just picking up on the point you sort of mentioned right at the end there regarding seasonality. So do you think that it's possible that the generation time might vary sort of seasonally because of changes in ventilation?
I think it's possible. I think it's changes in ventilation and behaviour. So if you've got everybody in an environment, if you've got settings where people all go indoors, they've got poorer ventilation and they're closer together, you've created conditions, I think, where the probability of transmission has gone up. I think you've also probably created conditions where the amount of virus people are exposed to has gone up. Now, what I don't know is whether that actually changes generation rate, or whether it changes. I guess it's whether, yeah, whether the whether you can assume that it's a cumulative effect of virus, or whether it's a, I suppose it's either cumulative or it's the probability that you've breathed in the unlucky particle, possibly. And I guess it comes down to what assumptions you make there, and we probably need to know a bit more about the in-host effects and the dose response to be able to work that out.
And so just picking up on the dose response stuff, are you starting to think about linking that to within host models?
Yes, there's some early work in the Protect National Core study that some colleagues at PHE and Manchester are leading on, which, yeah, starting to think about in-host models, and then hopefully we can try and connect them together. I do think this connecting together bit is, I think it's really important, but I think it's actually hard. And I mean, I guess that's one of the challenges with a pandemic and a crisis, is having that time to think about how to do that.
Do you think the challenge is beyond just the difficulty of speaking across disciplines, as Julia mentioned? And if that, so what other big challenges do you see?
I think there is. I think part of it is the cross-discipline, and probably getting the right people to work on it together. And a lot of those people are already crazy busy, I think. I do think there's probably some underlying mathematical development, model development needed as well. And I was talking about this with some colleagues earlier, in that we are in a position at the moment, I suppose, where we just need an answer. So we don't necessarily think through the most effective or efficient way to do something. We just plug it in and make it work. And but I think there probably is a step back where we need to say, was this the best way to do it? Or actually, are there other ways in which we could couple these things together that are a bit less clunky and a bit more representative?
Cool, well, great, thank you very much. So there aren't any more questions come through, and I've also been prodded that we should finish on time to give everyone a chance to have a break. So thank you very much, both Julia and Cath. I'll give you a clap since they can't be virtual. Yeah, as Julia pointed out, we are a fraction ahead of time. So if everyone wanted to take a 15-minute break now and maybe come back at about just after 5 to 4, and we'll try and get started bang on time. I've been told Robin has to get to his vaccine, so we have to finish our next one promptly. So yeah, everyone, if you want to take a quick break and grab a drink and things, and then we'll resume the next session just before 4. Thank you, everyone. Thanks, Cath. That was really